The next topic is interactions. And when you look at the interactions in ultra-cold gases, maybe you will have recollections from from the topic which may be familiar to you, resonant interactions of slow neutrons with atomic nuclei. Physics is very similar. I would remind typical distance is on the order of microns, and the atoms interact via electromagnetic potentials. So if we consider hydrogen-like atoms, this is four body interactions, four charged bodies, 2 ions and 2 electrons, two valence electrons, 1 valence electron per atom. So the potential is electrostatic, and the typical size of the potential, typical spatial extension of the potential is just on the order of 10 Bohr, about half a nanometer. And nevertheless, the atoms, so despite this very small range of the potential, the atoms can feel each other from very far apart. And this would be the peculiarity of low energy interactions. To understand the interactions, let's consider expansion of the interactions in the partial waves, in the partial spherical waves. So this is let's consider this is the wave function of a pair of atoms. R, it is the distance between the two atoms, and the solution, it's the state of the free unbound atoms plus the plane wave is for non-interacting atoms, plus the result of scattering, the outcoming scattered wave. And the potential can be, the potential for each partial wave can be written as effective potential, which is sum of the real potential plus the centrifugal potential. And by estimating the size of the centrifugal barrier, you can find that the centrifugal barrier is very high on the scale of the energies involved. Typical scale of this centrifugal barrier is a few millikelvin or tens of millikelvin, which is very high compared to the energies which are on the order of microkelvin or nanokelvin. It means only S wave participates in the interactions, which means S wave only head-on collisions without transfer of angular momentum during collision. So you can expand the plane wave, the free solution without potential in the spherical basis, and the scattering can only modify the coefficient in front of the zeroth order Bessel function. What does it mean? Let me remind a little bit of basics about scattering theory. So high partial waves remain unmodified. Only the zeroth harmonic is modified, and we are considering only spherically symmetric potentials because the atoms are hydrogen-like. They are spherically symmetric. They are in the lowest electronic state. So this solution for we're considering solution for the distance between two atoms. And only the lowest zeroth order Bessel function is modified. What the zeroth order Bessel function is? It is sine of kr, and I will leave space here, divided by r. So that's the Bessel function. It is oscillating, and it is going down as it oscillates. What happens as a result of interaction? Only phase shift is possible. It means this Bessel function can shift a little bit like this. So it can be pushed away from the origin, or it can be sucked into the origin. This is the whole result of the interactions. And you can write, and it is important to write down the scattering amplitude. The scattering amplitude, it's only the scattering amplitude for the S partial wave with the angular momentum L equals 0, and it can be represented as a in this form as a minus ik. K now it is not the wave vector of light. Light is not involved here in scattering anymore. We only consider two-body scattering, two atoms, nothing else, no other atoms around, just two atoms. So this is k, it is the momentum of the two atoms in the relative frame of motion, minus this constant, minus 1 over a. A, it is the S wave scattering length. And it is related to the phase shift. This amount, the zeroth order Bessel function shifts. It is just this amount A, the scattering length. And from this from this simple picture, you can see that A may be both positive and negative. For important quantity is the scattering cross section. It is just 4 pi times the square of the scattering amplitude, where in the very low energy limit, and as you for the lowest energies, momentum goes to 0, and the scattering cross section becomes just 4 pi times the square of the scattering length. But another limit is possible. A can go to infinity. Well, how to make A go to infinity? Of course, in this picture, A is finite, but for very low momentum, this period of the oscillations becomes very large, and together with the k goes to infinity, together with k goes to 0, A can become infinite. In the case of A equals infinity, the scattering amplitude is not defined by the scattering length anymore. It depends on the momentum. So for the infinite scattering length, the scattering amplitude is just 4 pi over the momentum squared. This will be important. This will be the limit of strong interactions. How to get big A? You can see to make atoms, this is very dilute gas. To make the atoms interact, you need very large scattering length A. You need very large cross section. And scattering length A, it can become much larger than this size of the electrostatic potential which acts between the atoms. In fact, in ultra-cold gas, it is possible to tune the scattering length. It can be set to any value you want. You can see in this graph, the scattering length is governed by, can be in some cases, which are most developed in present research. In those cases, the scattering length it is governed by the external magnetic field. By applying appropriate magnetic field, you can tune the scattering length to infinity. Or by choosing appropriate amount of external magnetic field, you can tune the scattering length to 0 and make non-interacting gas. How to tune the scattering length? First, let's consider tuning the scattering length in the frame of simple model disconnecting from experiment. The value of the scattering length A, it is connected to presence of a bound state in the interatomic potential. I'm reminding something I hope most of you know very well. In if there is a bound state in this interatomic potential, there should be the scattering length should be positive. Now let's make this potential a little bit shallower, like on this picture. If you make, you know that in 3 dimensions, in 2 shallow potentials, scattering length in 2 shallow potential, there is no bound state. If there is no bound state, the scattering length is necessarily negative. In this picture of the zeroth spherical Bessel function, it means negative scattering length means the wave function is sucked in. Oh, by the way, this modification of the Bessel function, it can be also described by adding a phase shift. So now the absolute value of the scattering length, it shows how big the cross section is, and the sign means whether interaction is attractive or repulsive. By getting rid of bound state, you can by getting rid of bound state, you can turn a repulsive interaction into attractive, despite this potential is always attractive. And how to get infinite scattering length? Infinite scattering length means very, very shallow bound state, which is exactly at 0 energy. The potential became deep enough so that the bound state just formed. What would be, and here I presented a very hard way of tuning interactions. It's changing depth of this interatomic potential. For electrostatic potential, it's very hard to change the depth. You would really break into the structure of an atom. There is a simpler way of tuning the scattering length, of tuning the interactions. And this way is called Fano-Feshbach resonance. Now, before explaining Fano-Feshbach resonance and scattering, I will go a little bit deeper into the internal structure of an atom. And I will use, as an example, I will use lithium-6 atom. Now, here I started specifying isotope with 6 nucleons. In ultra-cold atoms research, you can study fermions and you can study bosons. There is a very large choice of bosons. All alkali metals, they have bosons, but fermions are very rare. Only among alkali atoms, only lithium has fermionic isotope, and potassium has fermionic isotope. And potassium isotope has potassium 40. It has nearly 0 natural abundance. I think it's either 0.1 or 0.01%, something like those numbers. And only lithium has a more or less appreciable abundance, like 7%. Plus, it is very cheap to get pure lithium isotope because it was used in bombs. So lithium, it's among the cheapest pure isotopes you can get. Cheap you can get only fluorine for species like fluorine, because fluorine it's only one as isotope naturally. Okay, lithium. I have already announced lithium. For laser cooling, we considered a transition of the valence electron from 2s state into 2p states. For interactions, we only consider atom into the ground electronic state. So only the single valence electron is only in 2s electronic state. You can look deep into the structure of this state. this state has a structure because valence electron, it has spin. The spin is 1/2. It means there are 2s plus 1 states, 2 states. Also, lithium-6, it has a nuclear spin. The nuclear spin is 1. There are 2i plus 1, 3 states. So total there are 2 times 3, 6 ground states. And they appear by mixing those are hyperfine states. They are eigenstates of the operator of interaction between the electronic spin and nuclear spin. So there are a total of 6 states. And I will consider 2 states with the lowest energy. Those are the states in the finite magnetic field, so they are not degenerate, because I will consider situation with applied magnetic field. So those 2 states are not degenerate. I will consider those 2 states. In the highest magnetic field, those 2 states are diagonal, in the limit of infinite magnetic field, those 2 states become diagonal in the basis of nuclear spin and electronic spin. The electronic spin becomes -1/2, is -1/2 in those states, and the only projection of the nuclear spin differs. So in a sense, a mixture of ultra-cold lithium in these 2 states, it is very much like a gas of electrons. In a gas of electrons, you have 2 electrons, they have 2 spins. These are 2 internal states of the atoms. Of course, there are differences. One can even consider them minor, that electron has charge, lithium atom is neutral. But spin-wise, degeneracy-wise, those are very similar systems. Electron gas and atomic gas. Especially if electrons are neutralized by ionic lattice, it's those 2 systems, gas of ultra-cold lithium and electron gas, they're very similar. Okay, and I will consider interactions between lithium atoms in these 2 states. And I want to tune the value of the interaction. The interaction is only S-wave interaction, and I will be discussing tunability of the scattering length, and even changing sign of the sign of the interaction, changing from attractive interaction to repulsive. How this tuning is possible? Let's go slightly more into details of those 2 states, state 1 and state 2. So far, I announced that for infinite magnetic field, those states are very simple. Only 1 projection of electron spin and only 1 projection of the nuclear spin. At finite magnetic field, there is a little more complication. At finite magnetic field, there is small addition to the state. In state 1, this is that stretch state which I announced before, plus small admixture of orthogonal state. Opposite spin plus another projection of a nucleus. Same in state 2. And this just tiny admixture of other states is the key to tuning the interactions. Now let's consider how the interactions are tuned. This is the first point where we shall use the indistinguishability of particles. We are not considering big collection of particles, we are only considering interaction of 2 atoms. And let's say, this is 4-body interactions, interaction of 2 atoms. There are 2 ions plus 2 valence electrons, 1 valence electron for each atom. And those 2 valence electrons, they're indistinguishable particles, which means electron from atom 1 and electron from atom 2, they should be generally in a superposition of triplet electronic state and singlet electronic state. So the states of those two valence electrons are either triplet, both spins up, or singlet. So as you see from today, everything is about qubit notations. And there are different interaction potentials for the two situations when the two electrons are in the triplet state or singlet state. Maybe you remember from your undergraduate studies that there is no triplet molecular state for hydrogen. Why is that? So for this triplet state, the spins of two electrons, two fermions, are the same, which means the two electrons, they cannot be overlapping, they cannot be in the same place, which means these are the two ions, ion 1, ion 2. And electrons, they cannot be here in the middle. They are only somehow orbiting around. It means if electrons are not here in the middle, they cannot screen these two ions from repulsion. It means the triplet potential is shallower than the singlet potential. And what's even more important, for the triplet potential, you can tune the zero energy level. Look, these are the two potentials for the triplet state and for the singlet state of two electrons. Those curves, this axis is potential energy, and the horizontal axis is the distance between the particles. So the red curve, it is for the triplet configuration of the two valence electrons. They are triplet. They are with magnetic magnetic moments aligned. Oh, I'm sorry. It's aligned like this. So it's magnetic moments aligned, which means you can apply magnetic field and change the energy of the two atoms by changing the energy of the two electrons. So you can, by applying magnetic field, you can shift the energy of two atoms in the triplet states down. And you can tune, and suppose that we're considering scattering, so the two atoms, they're initially free. You can tune the energy of zero energy, free unbound state of the two atoms in resonance with the bound state in the singlet electronic channel. This singlet channel, it is even energetically inaccessible. At high magnetic field, it is much higher in the energy. But the two atoms, they get into the singlet state because it is in resonance with the unbound state. And this situation is very, very similar to the situation where just a simple potential has bound state at zero energy. Remember, in this situation, this is potential. And if the bound state is just at zero energy, this corresponds to the infinite scattering length. So by tuning in resonance, you get the infinite scattering length. And of course, And this situation where the bound state in the singlet potential is below the zero energy level, it means positive energy. So by applying magnetic field, this way it is possible to change the scatter length. That's the beauty of atoms, of ultra-cold atoms. It's the system which allows to tune interactions at will. And tune them continuously, because this is very simple to apply an external magnetic field. This again, that important graph, scattering length the scattering length versus the magnetic field. And those are just human size magnetic field. It's 1,000 Gauss. It's 0.1 Tesla. The producing such field even doesn't need superconducting magnets, which are used in MRI devices. Okay, now I hope I explained the basics of interactions, and we're in a position to start understanding. I'm in a position to start explaining collective effects with ultra-cold atoms. But before going completely into the effect of into many-body physics, let's reconsider again the evaporative cooling, achieving those low nanokelvin temperatures. Again, this graph about evaporation. So first we had a magneto-optical trap with resonant light, then reloaded atoms into a conservative trap created somehow with light. In this case, the trap is created in the focus of a laser beam, and cooled by evaporation. So now I hope I persuaded you that atoms can have a large cross section. Now they can collide, and most effective cooling was on the Feshbach resonance, which means the scattering length equals 0. I'm sorry, the scattering length equals infinity. The scattering length equals infinity, and if we try to write this expression, that's cross section for atom-atom collisions is 4 pi times the square of the scattering length. Of course, it's nuisance. It's prohibited by unitarity. The scattering length is the second option I gave you. It is 4 pi over k squared. And 1 over k, 1 over momentum, it's the de Broglie wavelength. It's a very natural picture. This, the particle cannot be bigger than its de Broglie wavelength. And the biggest possible cross-section is the square of a de Broglie wavelength for particles without exchanging angular momenta. So the fastest way of evaporation is to use Feshbach resonance to tune the scattering, the zero energy scattering length to infinity, which gives the biggest possible cross section, and evaporate. And in fact, it is possible to go down in temperature by evaporative cooling. It assumes that you lose some atoms, but the loss is not as huge. Let's consider experimental example. Starting with 1 million atoms at 300 microkelvin in such conservative trap, which gives phase space density 10 to the negative 4, and end up with losing 90% of atoms. It's high price to lose 90% of atoms. But to get atoms at 10 nanokelvin and with a phase space density 1. Of course, losing 90% of atoms is a lot, but look, it's 6 order of magnitude win in the density. It's somewhat reasonable price. And the important thing here is again the Feshbach resonance in the scattering of 2 atoms. This is phenomenon known from nuclear physics. The Feshbach, Hermann Feshbach presented this concept in the 40s in terms of scattering of nucleons. Similar concept was presented by Italian physicist Fano, and So this termed frequently Fano-Feshbach resonance, and I even heard undocumented rumor that Feshbach at the end of 90s, when those Feshbach resonances were studied in atomic physics, at that time he was an emeritus professor at MIT. He walked in somebody's office and asked, Feshbach asked to explain what are those Feshbach resonances which are now so popular in atomic physics. So now we got the interactions. Interactions are fully under our control. Before going into now the next step, we shall fully go into many-body physics. Before going into many-body physics, the short history of fermions and bosons. Now we know Bose gas is so important, but the history of Bose gases was not that lucky. For fermions, it was a beautiful situation from the very beginning. The concept of Fermi degeneracy, it was formulated in 1926. It was recognized immediately. Next year, Sommerfeld published his paper on the heat capacity of metals. He used this Fermi degeneracy concept to solve important problem. Because from the point of view of classical physics, the heat capacity of metal, it should be 6. Three comes from vibrations of the lattice. And 3, let's consider electrons as a classical gas. Classical gas of point-like particles, it also has heat capacity of 3. But Sommerfeld quickly recognized, using Fermi and Dirac's ideas, that electron gas is in the Fermi degenerate limit, and this is why it has almost no heat capacity. It has heat capacity on the order of temperature over the Fermi energy, and Fermi energy of electrons in solid state, it's 1,000 or 10,000 Kelvin, which gives room temperature a negligible value. Bose gases at the beginning did not seem to be so popular concept. Einstein published his paper in 1925 about Bose condensation of massive particles. And for quite a long time, there were no even physical system this concept could be applied for. Only in 1938, Kapitsa published his work on the superfluidity of liquid helium. And Fritz London came up with the idea that superfluidity of Bose of helium is connected to Bose-Einstein condensation of helium atoms. Landau immediately applied, saying that Fritz London presented a wrongful idea. It's again the art of misconceptions. Don't be afraid of discussing wrong ideas. Landau said that Fritz London was wrong, and Bose-Einstein condensate cannot be superfluid. Now we know that Bose-Einstein's condensates are superfluid, of course. Was Landau wrong? From position of that time, Landau was completely right. Because at that time, in 1938, people only knew about Bose-Einstein condensation of ideal gas. What was Landau's argument? Landau's argument was that ideal Bose gas, it has parabolic dispersion relation. And for superfluidity, as you know from Landau's criterion of superfluidity, the dispersion relation has to be either linear or convex. So Landau was right that the condensates known at that time could not be superfluids. And it turned only year 1947 when Bogolyubov considered interacting Bose gases. And Bogolyubov has shown that interactions change situation completely. Even the smallest interaction, even the smallest scattering length A, small non-zero positive A, changes the dispersion relation completely. It creates linear dispersion relation. So due to Bogolyubov, Bose condensates became superfluid. It was a long way of recognizing the idea of Bose-Einstein condensation. Okay, now let's turn back to ultra-cold atomic gases. And now we are in a position to reanalyze the first experiment on Bose-Einstein condensation. Okay, first, again, the point we shall be looking at, again, we shall reanalyze this picture. Is this true that all bosons in this experiment in Bose-Einstein condensate condensed in this lowest energy level? Now, from with the knowledge of interactions with the ultra-cold gases, let's first consider where those nice pictures came from. Let's look at the raw data presented in the 1995 paper. So the Bose gas in experiment was confined in a magnetic trap, not optical trap, not the trap created by focus of the laser beam, but in a magnetic trap of cigar shape. And the gas, the trap was instantaneously turned off, and then the gas started expanding from the trap. And it was photographed after a few milliseconds of expansion. And those are the photographs from the paper, photograph A, B, C. The color is not actual color, it means the column density along the line of sight. And the column density is coded into the color. Red, almost zero density. This bluish whitish is the highest density. So the highest temperatures, or with they did not know temperature in creating the gas. With the smallest amount of coolant, the gas was just expanding into a sphere, and then you could integrate this image along the vertical coordinate, and this would be this distribution of the density along one direction, just more or less Gaussian-looking distribution. Then with stronger coolant, first you can see a dense feature appeared in the center, and there is a peak on top of there is a peak on top of more or less Gaussian velocity distribution. Actually, there is a mistake on this graph. The trap is not oriented vertically, it is oriented horizontally. And the third graph, even sharper peak. And this is what those nice figures from the popular literatures represent. This is a more or less Gaussian distribution drawn in 3 dimensions. And this is the appearance of the Bose-Einstein condensation peak, or the peak later interpreted as a Bose-Einstein condensate. Now let's look at the role of the interactions. There is scattering length, which means particles interact. And you can write the interaction energy at the mean field level. This is the interaction energy. It's 4 pi times Planck's constant squared. A comes in. It's important that it comes in linearly. and divided by the mass and times the density. The scattering length of rubidium was used in that first experiment. The scattering length is not very high, 5 nanometers. But it is enough. You can calculate this interaction energy, and you can see the amount of interaction energy equals about the energy of the 5th energy level in the trapping potential. The trapping potential is nearly harmonic. Of 2 more minutes?
2 minutes.
Okay. So it means in this experiment, the atoms do not condense in the lowest energy state. It is indeed Bose condensate, but the atoms do occupy 5 one-particle levels in the potential. So Bose condensation is not a condensation into the single particle state. It's a condensation into the collective state. Indeed, remember I was telling you about the criticism produced by Yuri Kagan and colleagues. Indeed, with such interactions, even a classical gas can expand anisotropically. Remember, cigar-shaped cloud turned into a disk. Why this was a Bose-Einstein condensate? Why this was an immediate belief, and what were the rock-solid proofs that this is Bose-Einstein condensation? Immediate consequence was the appearance of this peak in the expansion of the gas, which means some atoms are expanding with low velocity. And the possible criticism, of course, this peak can be criticized, that, well, maybe this is non-equilibrium distribution, but after thermalization, something else could happen. And actually, those people who did this first experiment on Bose condensation, they produced another rock-solid proof of Bose-Einstein condensation, which I hope to discuss after the break.
Okay, thank you.
You have a question?
Yeah.
Yeah, may I answer the question before the break?
Of course.
Yeah. No, I was just wondering, so the peak area gets smaller or not? Or does the peak area stay the same?
Well, yeah, I hope you understand where those one-dimensional graphs come from. They come from those photographs, and these 3 curves is a result of integration along this direction. Yes, you are very right. You looked very careful at the data of Wieman and colleagues. And indeed, here this is pretty large peak, and this peak for the most condensed gas is pretty small. This is the reason for the smallness of this peak is all those density distributions, they correspond to deeper and deeper and deeper cooling. And the cooling is done by evaporation. So to achieve lower temperature, they had to evaporate more. They had to lose more atoms. So the peak gets smaller, or a little bit smaller, because they lose a number of atoms to get smaller temperature. So just smaller peak because of smaller number of atoms. Yeah. Okay, I think we are ready for the break. Okay, so we keep analyzing the experiments on Bose-Einstein condensation. So there was a great first experiment on Bose-Einstein condensation. There was definitely Bose-Einstein condensate there, though the picture which came from the experiment, it was open to criticism. There was a demand to a rock-solid proof of Bose-Einstein condensation. And that proof came. Where that proof came from? The proof came from the year 1995. The theory the proof was based on came from the same group of Yuri Kagan and colleagues. Remember, I told you about criticism of Yuri Kagan that classical gas can also expand anisotropically. The idea was the following: use inelastic collisions in a Bose gas. So first, what this inelastic collision means? Remember you saw a little note on the slide. The scattering length is 5 nanometers. It's important that it is positive. And shortly, you will appreciate that it's important for the scattering length to be positive. And even with I will give a historical example to appreciate the importance of positive scattering length. Positive scattering length means that there is a bound state in the interatomic potential. This is potential with which potential for interaction of the two atoms.
May I interrupt you for a second? Those who have been at excursion at Russian Quantum Center, they saw the last author of this paper. Yeah, it was 37 or whatever years ago. Okay.
Oh, Жора Шляпников. Oh, yeah. Georgy Всеволодович Шляпников is a legend in the field. In the English-speaking community, he is known as Gora Shlyapnikov. Okay, so this is the bound state, and it means two atoms can form a molecule. If there are two atoms cannot form a molecule, because to get from unbound state to the bound state, they have to give out some energy to somebody. Third body is needed. So three-body collision is needed to form into a bound state. So there are two atoms, no way to go to the bound state. The third guy comes in, and three atoms can collide. In fact, they can easily collide. There are bosons. They want to get together. The more bosons together, the better. So three bosons easily collide. And of course, the two atoms get bound. They get some kinetic energy, and they give out some kinetic energy to the third atom. So it means the gas chemical reaction goes inside the gas, and this chemical reaction is producing energy. And this kinetic energy makes atoms to go away from the trap. So this is the three-body inelastic process. So the idea of this paper of Yuri Kagan is that in the Bose-Einstein condensate, these inelastic, those inelastic collisions, the inelastic chemical reaction goes 6 times slower than in a classical gas. It's a huge difference. Where the number 6 comes from? It comes from classical. It comes from quantum statistics. It's the number of permutations of 3 different particles. Inside Bose-Einstein condensate, the number of entrance channel in this three-body collision is 6 times lower than in a classical gas, because in Bose-Einstein condensate, all bosons which want to participate in this reaction, all 3 bosons are in the same state. So fewer possibilities for the reaction. This was the idea, and the experiment was done by the same group which produced the first Bose-Einstein condensate. It was done by Carl Wieman and colleagues, and this is first one important formula. This is the rate of losses due to this three-body chemical reaction. So the loss rate dN by dt, n is the number of atoms, it's minus n times constant times, since this is a three-body process, it should involve average density in the power of 2. If it is a two-body process, the density would be in the power 1. If it is a one-body process, due to something happening inside the atom, it would be nothing after the coefficient k. And the coefficient k should be, coefficient k3 should be different by a factor of 6 in a classical gas and in the Bose condensate. And this is what they saw. On the vertical scale, they have this log of n. Here on the horizontal scale, they have average density squared integrated over time. And the slope is different in the Bose-Einstein condensate by a factor of 7.6. Of course, with quite significant error bar, but it very well agrees with a factor of predicted factor of 6, and very well disagrees with everything else. So this was the proof of Bose-Einstein condensation, which came from quantum statistics. There was another proof of rock-solid proof of Bose-Einstein condensation. It came from Wolfgang Ketterle and his colleagues. They observed interference of Bose-Einstein condensates. So the trap was also of cigar shape, but they used magnetic trap. I remember I was telling you always about optical traps in the beginning, and now I'm talking about magnetic traps. I will discuss the reason for that. So this was magnetic trap. It was separated in two parts, and two Bose-Einstein condensates formed. Then the trap was turned off, and two Bose-Einstein condensates, they started expanding, overlapping, and there was clear interference pattern. Of course, this picture after release, the clouds are much fatter because they expand in all directions. So those are the interference fringes. It means in the left side and in the right side of the trap, there were two macroscopic collective wave functions. So this is the formation appearance of collective wave function is identical to Bose-Einstein condensation. Now a historical note about importance of positive scattering length. In all experiments I told you about, all experiments on Bose-Einstein condensation, the scattering length was positive. So this was the first Bose-Einstein condensate. This was the first Bose-Einstein condensate. The group of Wolfgang Ketterle produced the third Bose-Einstein condensate. And then he also received the Nobel Prize. The Nobel Prize was given for to those who got the first Bose-Einstein condensate and the third Bose-Einstein condensate. There was also the second Bose-Einstein condensate in the history, which was produced by the group of Austin by this was produced by the group in Texas led by Randy Hewlett. And this was Bose-Einstein condensate with a negative scattering length. If you recall Bogolyubov's theory of Bose-Einstein condensation, maybe you know that Bogolyubov was also considering Bose-Einstein condensate with a positive scattering length. And there was a note that negative scattering length brings about attraction of bosons and collapse of Bose-Einstein condensate. So, nevertheless, Randy Hewlett and colleagues produced a Bose-Einstein condensate with negative scattering length. Why it existed? So the particles should have attracted each other. should have attracted each other, collide together, and get bound, form solid or clusters. Nevertheless, the condensate existed as stable. Why was that? Here I am applying Gross-Pitaevsky equation to this situation, assuming that the condensate has collective wave function. Look at the terms in this equation. First, this is diffractive term. Second, this is the trapping potential. And the third, it is the mean field. The scattering length A is negative, so this is negative term. Nevertheless, condensate does not collapse. This negative term is fought by this diffraction term. So this quantum diffraction of the joint macroscopic wave function now in this non-uniform condensate fought against this attractive term, and the condensate existed. But there was just some density limit to this condensate to exist. So if the density increases, density is psi squared. If the density of the condensate increases, then eventually this term becomes stronger than diffraction, and this condensate disappears. And this is again the data from the experiment, which is showing the existence of the condensate. And remember that peak of Bose-Einstein condensation, which you saw in the velocity. This is that peak in the interrupt images, like this smooth dashed curve. It's Gaussian shape for a classical gas, and there is a bulging on top of this shape, which assumes condensation. And there was difficulty in interpretation of the experiment. Initially, the condensate was initially so dense that they could not see this condensate. They reported, oh, we see something which looks like condensate, but then there was lots of criticism to this work, and it was, eventually the Nobel Prize was given to those who produced the first and third condensate. Okay, so let's continue. Oh, before, let me go back to a detail which I hope you will appreciate soon. Look at this little note. That the scattering length was 5 nanometers, and remember I was telling you about that the distance between the particles is on the order of a micron. And in principle, Feshbach resonances allow to produce a scattering length on the order of interparticle distance, and even a infinite scattering length in the limit of low energies. How come the authors of this first Nobel Bose-Einstein condensate were satisfied with just 5 nanometer scattering length? Why they did not use the Feshbach resonance? And why they used magnetic trap? The reason was that it was still year 1995, and many important questions were unresolved. Like I was telling you, that optical dipole trap, which forms in the focus of a laser beam, that it is perfectly stable and conservative. It was not that stable and conservative back in 1995. Optical dipole traps, they appeared at the end of 80s. But only by the year 99, they became stable and became suitable for producing ultra-cold gases. Why was that? There was very simple physics which defeated the advantages of optical dipole traps. It's even small noise in the lasers brought about heating of atoms in those dipole traps. Consider the following simple physics. For simplicity, this is potential of the optical dipole trap. And let it be For simplicity, let the potential be harmonic. And let's consider just a single particle oscillating in this potential. No quantum levels, just classical oscillations. And let's suppose the laser, which is producing this optical dipole trap, is a little bit unstable in the intensity, just 1% instability. The laser intensity means there is instability in the amount of this frequency omega. It means the trap is opening up and closing like this. And if this instability is the frequency 2 omega, there is a parametric resonance which transfers energy from oscillations of the trap walls to the motion of these trapped particles. And suppose this is white noise, but some amount of this white noise in the trap some amount of this white noise goes into the spectrum around 2 omega, and this just small fraction is enough to hit the atoms and prevent the optical dipole trap from being stable. This is why in the initial experiment magnetic traps were used, and this is why magnetic trap it is producing potential U equals minus mu times B. Mu, it is the magnetic moment of an atom. Well, all alkali atoms, they have magnetic moment because they have one valence electron. It is magnetic moment of an atom. Basically, this is magnetic moment of this electron, which equals to the Bohr magneton. So magnetic field was already used up for producing a trap, and it was not possible to apply additional magnetic field for tuning Feshbach resonances. If additional magnetic field were applied, it would have ruined the trap. Now the question is, how evaporation was performed inside such a trap? First, you can notice the scattering length amount, which is 5 nanometers, not very large amount. On Feshbach resonance, the evaporation takes a few seconds. There are even protocol for a fraction of a second evaporation. In that initial Nobel Prize experiment on Bose-Einstein condensation, the evaporation took 70 seconds. How to perform evaporation? In the optical trap, this is very simple. This is the number of atoms versus their velocity. This is the velocity distribution. Let's consider classical for simplicity. If the temperature at some point the temperature becomes low, very low, and the tail is very much inside the trap, and this is cutoff velocity. Above this cutoff velocity, the atoms are lost. If this cutoff velocity is very, very high, the atoms are lost exponentially slow, and there is no way to finish evaporation in any reasonable amount of time. In optical trap, it's very simple. You lower the power of your laser, and this shifts the border of evaporation below. In magnetic traps, it's very different. It's hard to manipulate magnetic fields like this. But there was another idea. Let's consider the trapping potential for magnetic trap. It's also parabolic. It's parabolic for trapped state, let's say with a projection -2. It's projection of the total angular momentum of the whole atom. And it is possible to, but see magnetic field, the potential, it is minus mu times B. And potential depends on the state the atom is in. So for states with other, it's plus 2. For states with negative projections, the same profile of the magnetic field is not attractive, it is repulsive. So it's repulsive for MF equals -1, and it is even more repulsive for MF equals -2. So if you apply also quickly oscillating transverse magnetic field, then you can move the atoms from trapped state to untrapped state. It's oscillating magnetic field. And by varying the frequency of this oscillating magnetic field, it is possible to choose whether to remove atoms from the trap or from the places close to the center. This was the idea of evaporation in magnetic traps. So the magnetic trap was a great tool at that time. It produced interesting results, but it did not allow the use of Feshbach resonance. The era of Feshbach resonances came later. Okay, now let's start. I've already told you basics about bosons. Now let's look at the fermions. So the first Bose-Einstein condensate was produced in 1995. Fermions came later. And the first experiment with fermions is done in the year 1999. And it was produced in a magnetic trap. It was again produced in a magnetic trap. So the trapping potential is again magnetic moment times the value of the magnetic field. And the next important step was made in 2002. The scattering, the degenerate Fermi gas was produced. It was produced in an optical dipole trap. And this allowed the application of the Feshbach resonances, because magnetic field in this situation is a free parameter. So if you have optical dipole trap, you can independently apply magnetic field and tune the scattering properties. With the use of optical traps, it was possible to explore the whole possibility of Feshbach resonances. And let's see what we can get from the Feshbach resonance. Let's suppose we created a Fermi gas with infinite scattering length. And also notice it can be plus infinity scattering length and minus infinity. We shall later consider and figure out whether plus infinity and minus infinity is the same or not. Now let's consider Fermi gas with a scattering length equals minus infinity. Let's consider physical quantities, physical consequences of this large and negative scattering length. Okay, so minus infinity. Let's first analyze this physical system at the mean field level. At the mean field level, and let's approach the situation naively. Let's write down the mean field, the interaction energy, in the form which is known for small scattering length, where scattering length is just a small perturbation. So let's write it down. Interaction energy is proportional to the A, the scattering length, and the density. And let's write down the energy balance equation. From the energy balance equation, we can see two effects. First, there is there is Fermi energy in the system. Only one and by the way, we are considering a Fermi gas consistent with atoms in two spin states, spin up and spin down. This is why S-wave interactions are possible. Otherwise, there is no S-wave interactions. So this is somewhat similar to electronic gas in solid-state systems. So, and those, so each atom interacts only with the other species with the opposite scattering length. So this is the situation we are considering. So each species, both spin up atoms and spin down atoms, they both have a Fermi pressure, which does not which holds the gas against collapse. And also there is this interaction term. And as you, in this very naive picture, as A goes to minus infinity, of course the attraction term should win. This is negative energy. It should cause attraction in the gas, and all our atoms should just glue together. As they glue together, three-body collisions go on. S-wave interaction breaks down. They all just stick together, form a solid. So in a naive picture, gas with a large negative scattering length is impossible. Let's now try to fix this picture and save this physical system from being abandoned or neglected. So the naive picture says collapse. Let's again recall the expression for the scattering amplitude. The scattering amplitude consists of the term dependent on the scattering length and momentum of the relative motion of two particles. And let's just do order of magnitude analysis. Here at the mean field level, I will only do the order of magnitude analysis. So this is this A is infinity, so the scattering length only equals 1 over the momentum. And in the Fermi system, the scale of momentum is the Fermi momentum. Therefore, the scattering amplitude does not become infinite, and for the instead of in this expression for the interaction energy, instead of zero energy scattering length, we should substitute some effective scattering length, which is on the order of 1 over momentum. And therefore, and we have one more number here in the expression for the interaction is the density n. And density is on the order of Fermi momentum cubed. Therefore, for the interaction energy, we have just that is on the order of magnitude of minus Fermi energy. As a result, in this tragic equation, which suggests collapse of the system, for the energy, we should substitute this effective energy, which is on the order of Fermi energy. So when interactions are S-wave and maximally strong as possible, the situation at the first glance remains uncertain. It is hard to say whether the gas is stable or it will collapse. It's not clear which term would win. So the interaction term, it occurs, it is on the order of the Fermi energy as well. So, and this motivates doing experiment. Before coming to probably the system will not collapse. Let's stay at this point. And let's look at the importance of this atomic system. Let's look at the connection of an atomic system to the other fields of physics. So I'm considering now a gas of fermions. what are other field of physics where we have a gas of fermions? Basically, I listed them here. Well, high temperature superconductors and nuclear matter. Neutrons are also fermions. And they are very close to the approximation I'm considering. I'm considering fermions with infinitely large S-wave scattering length. And this is this situation is very close to the neutron matter, like, for example, neutron matter in the crust of a neutron star. Because what we have on a neutron star, and also in heavy nuclei, it's also fermions. And neutrons, for the neutrons, they are also dominating collisions. Dominating collisions are S-waves. There are also P-wave scattering, but S-wave scattering is very strong. And for the neutrons, the scattering length is -19 Fermi. Is it a lot or it is little? Well, let's compare to the size of the scattering potential. The size of the scattering potential is 2 Fermi. So it's very similar to the atoms. In the atoms, the scattering length is bigger than the interaction potential, and same in the fermions. And with big enough density, we're in the same limit that the scattering length is much bigger than the density. And this is the similarity of our and this is the similarity of the two systems. So it is not, of course, it is not possible to say that they are identical, but it is usual in physics. They bear clear similarity, despite the fact that energies and densities are very different. They are many orders of magnitude different. With high temperature superconductivity, this is also, there is some similarity, but not as deep. The interactions in high temperature superconductors, there are lots of experts here. The interaction is dominantly D wave instead of S wave with ultra cold atoms, but it is also a fermionic system. Okay, so puzzles. I guess how I'm doing time-wise. Oh, okay, we shall touch those questions maybe in those 10 minutes. Whether the system with strong interaction it is stable. This is the first puzzle we shall consider with a Fermi gas.
What's the meaning of this energy scale?
It's the Fermi energy. It's the Fermi energy which you can get on a neutron star from that basic problem that Pauli exclusion principle is fighting against gravity, does not allow the neutron star to keep shrinking. The second question, and I'm again considering A infinitely negative, is a superfluidity. And this question relates both to neutrons in a neutron star and to ultra cold atoms in the trap. This is the theory you know. This is the Hamiltonian you may know from the Bardeen-Cooper-Schrieffer of superfluidity. And look, in this Hamiltonian, there is nothing about charge of electrons. There is nothing about crystalline lattice in the superconductor. This is only this Hamiltonian is only about a gas of fermions. It's only about a gas of fermions with spin up and spin down, and they have also S-wave interactions with some value. So ultra cold atoms perfectly fall under this Hamiltonian. Of course, the Bardeen-Cooper-Schrieffer solution, it is only for very small a. The Bardeen-Cooper-Schrieffer solution is for absolute value of a much less than the interparticle distance. But this is the solution, and the Hamiltonian has no restriction on the a value. I would remind you the solution for the critical temperature. The order of magnitude for the critical temperature for superconductivity or for superfluidity if there is no charge, it's exponential in a KFA parameter. But if you set a to infinity, then you may ask a question: what is you may see that the critical temperature for superfluidity is on the order of the Fermi energy. Of course, there is a question about numerical coefficient in front of this exponent, but at least for infinite a, the critical temperature is not exponentially suppressed. And the question is it possible to get superfluidity at the level on the order of the Fermi energy?
In the conventional theories of conductors, there is dipole frequency, not Fermi energy.
Well,
why should it be so in Fermi gas?
There is a question of, first, it's a very good question why it is good. Look at this Hamiltonian. There is no lattice. There is no ionic. There is no lattice of ions in this Hamiltonian. So intrinsically, how the problem is posed, there is no Debye frequency in the. There is no Debye frequency in the Hamiltonian. It's something from outside the theory, because where the Debye frequency appears to get rid of as an ultraviolet cutoff. And another way to handle the problem is to renormalize this coefficient V2 to get rid of divergence. What the problem of this V2 coefficient? It's this V2 coefficient here. Let's suppose we take it as a constant. We take it as a constant. It means the interaction between the two atoms is a delta function. This is the interaction potential for the two atoms. It's very nice, but it is problematic when you if you would try to apply it in the second Born approximation. It would give you infinite energy shifts. So it has to be renormalized. It has to be either renormalized, or you should get rid of this. The problem of this potential, it can scatter particles with infinite momentum. Any real scatterer is transparent for infinite momentum particles. Delta functions scatter even particles with infinite momentum. So there should be some way to get rid of infinite momenta. And one way is to introduce the cutoff at the Debye frequency, which gives you Debye frequency coefficient here. Another way is to renormalize this scattering potential to get rid of divergence in the second Born approximation. And this way you get the Fermi energy in the solution. So it is possible to 5 more minutes. So it is possible to get a solution without Debye frequency. So there is a possibility, there is a temptation to give a superfluidity at about the Fermi energy, even though this Fermi energy is nanokelvin or hundreds of nanokelvin. A real temperature would be small, but it's a lot in units of EF. For example, for cuprates, the highest critical temperature was just 1% of the Fermi energies. Well, it was obtained in, I think it was obtained in mono layers. Oh no, this was in several layers of cuprates obtained in 1991. Okay, so these are the two questions I'm posting: the stability of the Fermi system with the infinite interactions and the superfluidity. Okay, and I would rather continue with those two questions with bigger details on the next lecture, if you don't mind.